right? I thought there'd be data. Is anyone out there?
Okay, by Wednesday, we're going to be into our full-on general hypothesis testing where we're not restricted to these little not equals, less than, greater than, and it's going to really open up a lot of tests for us, but we're not quite there yet. I have to do just a little bit more about some of these special statistics, specifically minimal sufficient statistics and something known as ancillary statistics. So just to kind of wrap up what we were talking about last time about complete statistics and minimal sufficient statistics, and we saw Bahador's theorem, which said that if you have a statistic that is complete and sufficient, then it is minimal sufficient. Okay, so just a couple of three really quick examples to kind of get out of the way of kind of special things like a minimal sufficient statistic that is not complete, for example. So my first example is something that is sufficient but not complete. And this is almost always the full sample. That's always a great example of this. And that is assuming that your complete statistic is kind of corresponding to your minimal sufficient one. So you should have come down by several dimensions. So this is not, I guess, guaranteed, but probably, depending on the problem, this is sufficient for the data and not minimal sufficient. And so not complete, because if it was sufficient and complete, it would be minimal sufficient. Okay, how about something that is complete, but not sufficient? I have one. That's right. How about S equals 7? So if I take any function of 7 that has to be 0, then the function is going to be 0 itself. No. I have to do the for all theta thing. The expected value, it's just complete, but hardly sufficient. Okay, so this one is maybe the most interesting one, and that is minimal sufficient, but not complete. Because most of the times, these are the same thing, but not complete. So an example of this would be to look at the normal distribution with mean mu and variance mu squared. So if you, we can show, and I will tell you how to do it today, because right after this, I have a theorem that helps you identify minimal sufficient statistics. So we will see that the vector, the sum of the x's and the sum of the x's squared is minimal sufficient. So just hold off on that a little bit. I'll convince you right after this, but I just want to show you, we can show now that it's not complete. So the quickest way to do this would be to say, I can write the sample variance as a function of those two guys, right? Our regular sample variance is the sum of the xi minus x bar squared over n minus 1, which after a little bit of algebra can be written as the sum of the xi squareds minus the sum of the xi all squared over n minus 1. And so again, the sample variance is a function of these two guys. So the expected value of the sample variance is the true variance, which in this case is mu squared, and the expected value of the sum of the xi squared, if you pull the n out because it's a linear operator, so I don't need independence or anything, then I have the expected value of xi squared, and I can do our trick. I can write that as the variance of xi plus the expected value of xi all squared. And so that is going to be the variance plus the expected value all squared. And so I get 2n mu squared. I didn't write out the intermediate step, which was to say this expected value of the xi squared is the variance of x plus the expected value all squared. Okay, so can I put these guys together? I think I can, hopefully, to find a function of these guys whose expected value is going to be 0, but the function itself is not necessarily 0 with probability 1. So I'm going to look at well, here's a function. So let's check this out. The expected value of 2ns squared minus the sum of the xi squared is going to be 0. So we have done it. I guess we have to convince ourselves that the function is not identically 0. This is really I need to write this out just a little bit differently. So this is 2n, the sum of the xi squared minus the sum of the xi all squared over n minus 1 minus the sum of xi all squared. So this is like looking at the function g of xy being 2n x minus y squared over n minus 1 minus x. And that is not the 0 function, even though the expected value when you plug in these statistics gives you 0. This is more for your entertainment. I don't know, I've never seen this come up on a prelim or anything. Are you entertained? All right, so this was supposed to be an example of something that is minimal sufficient and yet not complete. So we showed the not complete part because we found a function of the vector of statistics whose expected value is 0, and it didn't imply that the function itself had to be 0. Not complete. But how do we show it's minimal sufficient? Because right now, our only way to show minimal sufficiency is Bahadur's theorem, which is to find something that is sufficient and complete, and then we get minimal sufficiency. But this isn't complete, so that's not going to work here. So I have a criterion, a theorem, a claim, a thing to show minimal sufficiency. So I don't know. This is never really called anything other than, I'm going to write criterion. Criterion for minimal sufficiency or theorem. I don't know. So suppose we have x1 through xn with a joint PDF f of the vector x and theta, which probably came from multiplying individual IID kinds of things together, but doesn't have to. So I've got x1 through xn with PDF f of the vector x and some theta. And suppose that t, capital T, which is going to be a function t of the capital X vector, is a statistic satisfying the following. So the thing we need to satisfy is if we look at a ratio of the joint PDF with x's plugged in over the PDF with some y's plugged in, if this is theta free, if and only if t of the vector x equals t of y, then t is a minimal sufficient statistic. I'm going to prove this, but every time I prove this, it gives me a massive headache. Hopefully you'll get a massive headache too. It's not that long, so it's a fast inducing of a massive headache. Okay, so actually before doing that, because I'm trying to put it off, How would we use this? I can use it on the previous example. That would be how I would show that that statistic, the sum of the x's and the sum of the x's squared, are minimal sufficient. But while I'm here, let's just do something else as well. So how about some IID Poissons with some parameter lambda? So the joint PDF here is e to the minus n lambda, lambda to the sum of the xi over the product of xi factorial, and then, yeah, indicators if you want. What's going to happen to the indicators is the same thing that's going to happen to this product of the xi factorials. It's not going to cancel. I just don't feel like writing that indicator. All right, yeah, I should. The indicator is I goes from 1 to n of saying that each xi is in the set 0, 1, 2 on up. So if I form this ratio, f of the vector x and theta over f of a vector of y's and theta, I mean lambda, then I get stuff. I get the e's are going to cancel in this ratio, and the x stuff is just going to sit there, and we get, so I get a product as I goes from 1 to n of the indicator of the xi over the product as I goes from 1 to n of the xi factorial over the same thing with y's, same thing with the y's, and then lambda to the sum of the x's minus the sum of the y's. And so there's no parameter in this first part, especially if you understood what I meant by the same thing with the y's. There's parameter in this part, but it will disappear and this thing will become lambda free if and only if the sum of the x's is equal to the sum of the y's. So this is lambda free if and only if the sum of the x's is equal to the sum of the y's. And so from this criterion or whatever it's called, t of x defined to be the sum of the x's is a minimal sufficient statistic once we prove this. Okay, so you could use this same theorem on the normal example as well, but let's get the proof out of the way so we can talk about ancillary statistics and Basso's theorem. I'll just give you a little hint. I'm really putting off this proof. So Basso's theorem is a way to show that things are independent, and it is so slick. And you can hardly ever use it in real life, but when you do, you just feel like the ultimate boss. Like people around you are writing out horrible joint PDFs, and you're just like, oh, Basso's theorem. It's a really awesome way to show independence if you can make it work. So let's prove this criterion or theorem or whatever. So 2 parts here. The main part is to prove sufficiency. So I'll call this A. Okay, so I am going to suppose, I don't want to rewrite this, I'm going to suppose that T is a statistic satisfying that if and only if property. And I want to show that T is therefore sufficient. So assume the F over F is theta free if and only if Tx equals Ty. And that F over F really means F at the vector X and F at the vector Y. Okay, so my first step is I'm going to partition the support of the joint PDF. So that is the place where the joint PDF is non-zero. I'm going to partition it into a bunch of disjoint sets that their union will make up the whole support. I'm going to partition the support again, that's the place where this PDF is interesting and non-zero, of the joint PDF into non-empty sets. I'm going to call them A sub t, and I'm going to define A sub t to be all of the x vectors for which t of x equals this value little t that I've used as the subscript. I mean, if little t is not something that the function t takes on, then that's not one of your sets. This is why they're all assumed to be non-empty. Okay, so for each of these AT, I'm going to choose and fix one element in there that is going to be a representative of this set. Choose and fix one element of AT, and I'm going to call it the vector x sub t. And it doesn't matter which one you choose, but just choose and fix one for us to go forward in this proof.
So am I understanding that A is the pre-image of little t?
Yeah.
Okay.
Yeah, that's right. Okay, so based on this choice, we have a couple of things. We have that the t function of this x sub t is equal to little t, because everything in that set goes through the function t and gives you little t. And this is just one element in that set. And we also have that once these elements are fixed, the x vector sub t is a function of t. In other words, it is determinable by knowing t. Given t, you go into the set AT and you pull out that fixed element. So as a function of t, i.e. xt is determined. We partition the set and we fixed an element to represent the set. And so the third thing I'm going to do is to note that for any vector x in the support, the vector x sub t of the vector x, little inception like here, is going to be in the same partition as x. So is going to be in the same partition set. I mean, the same sort of A set as x. The reason is that if you take an x in one of the partition sets, AT, then this implies, and actually both ways, implies that the function little t of x is equal to this fixed t. And that's going to be true if and only if the x vector sub little t of x is equal to the x vector at t, which is in AT. That's, I think, maybe the worst part of it, actually, so it's not that bad. Now that I look at it again, it just feels really weird and circular. Okay, so my fourth step is going to be, remember, I'm assuming that t is a statistic such that if that ratio of PDFs is theta free, then t of x has to equal t of y. So, okay, so, suppose that f of x and theta over f of y, and theta is theta free No, that's actually the condition. We started with a statistic t that, no, I can't guarantee that that's going to be theta free. I can just say if that's theta free, then t of x has to equal t of y. So yeah, I'm going to suppose it's theta free. And so I'll call it, say, h of x. That's a function that does not depend on theta. So this is going to imply that, I'm so sorry, this whole step is wrong. Sorry. I need to use the step I just wrote down. We have that the x vector sub t of the vector x is in the same partition set as x. So this means that f of the x of x and theta over f of the vector x sub t of x and theta. These are both things going to be in the A set. So these are both things that map to little t under x. And so I want to say that this means that this ratio I want to say that this ratio is theta free. And if I can, I think I can, let me write this down and then back up and try to justify this. So if this is theta free, say some h of x, then I have that the joint PDF for the x's and theta is some h of the vector x times f of x sub t of x and theta, and then by the factorization criterion for sufficiency, I have that actually I also have to include, and the fact that x of t, x sub t of x is a function of t. That's something we established back up here. That means that that means that this guy is a function of t. It's a function of t equals, it's function of t of the vector little x, which implies by the factorization criterion that t defined to be t of the large x is sufficient. Now, one thing that I passed by was that I wanted to assume that this ratio was theta free in order to get that t was sufficient. And I'm not sure why I know that at this point.
Is
yeah.
that one direction of it? Or we proved that this equivalence implies sufficiency? Or
Yeah, we're proving that if these are equivalent, then we get sufficiency. But my question right now is the condition in the criterion says that if this is theta free, then T of this must equal T of, oh, it does. It does. So let me get a different color. I get it. These guys map to the same thing under T. So these guys satisfy T of the vector X is equal to T of the vector X sub T of the vector X. You have a headache yet? And so because they are equal when going through the function T, under the assumption of the criterion, that implies that this is theta free. So I'm using the right direction of that property. Does that make sense?
Right. You approved these things are equivalent. We defined this equivalence class so that the right-hand side was satisfied, which lets us assume the left-hand side is an
Yes.
approved sufficiency.
Yeah. And then everything going forward is the same because I went forward assuming this big circle. And so again, I get that big circle because I look at like this guy and this guy. I'm not saying they're the same, but they're in the same class. And that means that if you put them through the function T, they map to the same thing. And so therefore, I've got, where is it? I've got this holding, which implies that this holds. So I get to say that this thing in the circle is correct, that that ratio is theta free. And if the ratio is theta free, I call it something like h of x with no theta. And then I write this as h of x times this. And then I'm using the factorization criterion to look in there and find a sufficient statistic. And this is a function of t of x. It's actually a function of x of t of x, but way back at the beginning, we showed that the vector x sub t is completely determined by t. So in other words, the vector x sub t is a function of t. We did it.
So why did we use the other direction in that inequality, in that equivalence there? I feel like we just went one direction. So.
Yeah, we only show sufficiency, and now we have to show minimal sufficiency. So part A of my proof was to show sufficiency, and now let's show the minimal part. What time is it? Minimal part. Yeah, this is going to use that direction. So I've got this T, and we've shown it's sufficient, and we want to show it's minimal sufficient. So I'm going to let S be some other sufficient statistic. Any other sufficient statistic. And we need to show, I hope I don't get this backwards again. We need to show that a statistic is minimal sufficient if it is sufficient and a function of every other sufficient statistic. So we need to show that T of x is a function of S of x. Okay, so that would be enough to show minimal sufficiency because I just took any sufficient statistic. And T is the thing we're claiming is minimal sufficient. Okay, so in order to show this is still part of a long parenthetical remark. We will have this like a function is something that defines, it can't give you two outcomes when you plug in the same thing, right? You can't plug in x and get 5 and also plug in x and get 8. And that's how you define a function. So we'll have this if we can show that S of x equals S of y is going to imply that T of x is equal to T of y. Did I ever tell you about my double? Did I tell you about my double lines at the end of a proof where I'm not at the end of this proof? Every time I write that at the end of a proof, in my head, I'm saying happiness ensues. I don't know why. I just can't get that out of my head. I'm so happy at the end of every proof. Okay, so let's do it. Suppose that the vector little s of little x is equal to the vector little s of the vector little y. So since s is sufficient, I can use the factorization criterion, and we can write the joint PDF as some h of x. So this is a separate part of the proof, and I am reusing letters. So this does not mean the h of x from before, times some g of s of x and theta for some h and g. Okay, so the ratio of fx and theta over fy and theta for any x and y is just going to be this with x's plugged in over that thing I circled with y's plugged in. But because I'm under the assumption that s of little x is equal to s of little y, the g parts of those are going to be identical. So plug that stuff in, and you're left with only h of x over h of y, which is theta free. I feel like I'm using the same direction again. I don't think I am. Thus, we have that t of x is equal to t of y by the assumption in the setup. So by the setup here. And we got that from assuming that s of x is equal to s of little y, i.e. s of the vector x is equal to s of the vector y, gave us that t of the vector x is equal to t of the vector y. Yeah, we did use the other direction. And so s was arbitrary but sufficient. And showing this was enough for us to show that t has to be a function of s. So t is minimal sufficient. And then happiness ensues. More than ever. I just wanted to be done with that. Okay, not only were we able to prove it, but we were able to use it to quickly find something minimal sufficient for the Poisson, and you can go back and apply it to that normal mu squared example. All right, we're done with this stuff. Now it gets fun again. This is new stuff. Still about statistics, but no more minimal sufficiency. So the first thing I want to do is define for you an ancillary statistic. A statistic, T, is ancillary if its distribution is parameter free. As an example, let's take the normal distribution, x1 through xn, IID normal, mu, and let's fix the variance at 5. Then n minus 1 times the sample variance s squared over 5 is chi-squared n minus 1. So n minus 1 s squared over 5 is ancillary. Why are we going to care about these things? Because sufficient statistics have like all of the information about theta in them, and ancillary statistics have no information about the parameter theta in them. So they seem in this sense kind of opposite things. And I would love to be able to tell you that a sufficient statistic and an ancillary statistic is always independent. Unfortunately, that's not true. But I will have two theorems for you. The first one is that if you have something that's sufficient and another statistic that is independent of your original statistic, that second one is necessarily ancillary. To go the other way, if I have something sufficient and ancillary, that's not enough to get independence unless I also throw in completeness. And that is a really famous theorem known as Bassu's theorem, which is we're going to hit next time. Not done, but we're not going to make it to that. Bassu's theorem. And so again, if you have something that is sufficient and complete and another statistic that is ancillary, then they are independent. And this is so cool when it works out for you. When you notice something like this happening and you can say, I know these are independent, and you know your roommate is working out these horrible Jacobians. And we can do this because I can give you a large class of statistics right off the bat that we know are ancillary. So if we can find ancillary things very easily, we know how to find complete and sufficient things, and we can say these guys are independent, and happiness ensues. So I'm just going to get a little bit into this. Let me give one more example. And this one will just be believable, but why is it true? And what we're about to go into will help you show why this is true. So suppose I have x1 through xn IID uniform on the interval from theta to theta plus 1. So if I look at the sample range, which is defined to be the max minus the min, I claim that this is ancillary. Is ancillary, which I think is highly believable, right? You know, you've got an interval starting somewhere and that's moving around, but the length of the interval is not. So the distance between the max and min it's believable that it's not going to depend on theta. But how can we figure that out? Because theta in this case is known as a location parameter. So a couple of definitions for you. Suppose that your PDF for whatever model you're looking at, it's a function of x and theta, and suppose this can be written as theta times some f naught of theta x, where f naught does not depend on theta. If your PDF can be written this way, we call theta a scale parameter, which is what I'm trying to define here. For example, the exponential distribution, exponential with rate equal to lambda, we can get the PDF from lambda f naught lambda x, where f naught is just the exponential distribution PDF with parameter 1. And yeah, indicators.
Question.
Oh yeah,
So that's f naught of theta times x, not comma x, right?
that's right. Yeah, that's a really good point because I always have commas or semicolons there. That's a multiplication. When you have things like 1 over theta, f naught, x over theta, theta is actually known as an inverse scale parameter. So the beta in our gamma distribution is an inverse scale parameter, whereas the beta parameter in some other people's gamma distribution is a scale parameter, while ours is inverse scale. But they're all kind of scale parameters anyway. So this would be called an inverse scale parameter. Okay, why do we care? Because I'm going to define for you a scale invariant statistic And then I'm going to reach the conclusion that if you're dealing with a scale parameter, any scale invariant statistic is necessarily ancillary. So I didn't mean to do this. I meant to start with location parameters, but I'm going to go with it. So a statistic t, which is some t of a vector x, is scale invariant if for any c, for any constant c, the function t of little x1 through little xn is equal to the function t of little x1 plus c out through little xn plus c, and c could be negative. And so if that's true, we say that the statistic is scale invariant. And so this is not the example I wanted. I wanted to start with something else known as a location parameter to talk about that uniform example. But as an example here, maybe you've got a random sample x1 through xn, and the statistic x bar over the minimum, just to make something up, is scale invariant because, oh gosh, that is wrong.
Yeah,
I
that's the
mixed, yeah,
location,
I
right? Okay.
mixed up the scale and the location stuff. So in the definition of scale invariant, I need to multiply these guys. Sorry about that. So then this is scale invariant because if you multiply everything in your sample by C, then your sample mean ends up multiplied by C. And everything, oh, this needs a C greater than 0. I didn't need that in the location case. But if C is greater than 0 here, then the minimum of all of the values multiplied by C is just the original value, the original minimum multiplied by C. So I am out of time, but like if I let y be like yi be c times xi, then the sample mean for y is just c times the sample mean for x, and the minimum for y is c times the minimum for x. And if I divide this by this, I get the same thing as dividing this by this. So it's a scale invariant statistic, this guy. And so what we're going to prove next time is that if you have a scale parameter, any scale invariant statistic is ancillary. And same thing with this other thing called a location parameter. So I am out of time. I thank you. And next time, Basu's theorem, which is so awesome when it works. You are going to have a moment like this years from now, where Basu's theorem is going to help you prove independence. So thank you.